Hi everyone, and welcome to a new episode of the Allplane Podcast, where we talk with the movers and shakers redefining the future of commercial aviation. And before we dive into today's conversation, I would like to remind you that all previous episodes of this podcast, along with many other interesting stories about innovation and sustainability in aviation, are available on the Allplane website at allplane.tv, ALLPLANE.tv. I would also like to invite you to subscribe to our newsletter, which is focusing on sustainability in the aviation industry. You can find the subscription link right on our website, Allplane.tv. And now let's get into today's episode. If you have been following the electric aviation scene, you are possibly familiar with the main challenges that electrification poses. There are actually quite a few interesting and very promising fully electric aircraft projects out there, and we have actually seen quite a few of them here on this podcast. But as you know, most of them are targeting the small aircraft market, whether it's general aviation or urban air mobility or regional air travel. Now, the market segment that is typically absent from this discussion is the one that is actually the largest and the most significant when it comes to reducing aviation's carbon emissions. This is the mid-size to large airliner segment. In short, the type of aircraft that most people fly on when they travel between two cities on a regular airline. But difficult doesn't mean impossible. What if fully electric propulsion for large aircraft was, after all, way more feasible than has traditionally been thought? A team in the Netherlands has set out to do precisely that. Our guest today is Daniel Rosen Jacobson, co-founder and co-CEO of Elysian Aircraft. Elysian Aircraft is a Dutch startup that is working on a battery electric aircraft that could carry up to 90 passengers. This is a concept that has been validated by research conducted at Technical University of Delft, one of Europe's top engineering research centers. In fact, 2 research papers have come out of this collaboration between Elysian Aircraft and Technical University of Delft. They establish the basis for the feasibility of large-scale battery electric aircraft, and Daniel and his team are working to take this idea from the realm of theoretical science to the real world. In this endeavor, Daniel has counted with the support of Panta Holdings, a Dutch investment firm of which he is a board member as well, and which is the owner of several businesses in the aerospace industry, including what's left of the legendary Fokker brand, one of Europe's most iconic aircraft makers with a history that goes all the way back to the very early years of aviation. So in this episode, we will talk with Daniel about the findings and assumptions that are behind the bold bet that Elysian Aircraft is making in developing a 90-seater aircraft with a range of nearly 1,000 kilometers, powered entirely by electric batteries. We will also review the main features of the E9X, which is the name of this future aircraft, as well as the current status of this project and the roadmap ahead. When and how can we then expect to fly electric aircraft on major trunk routes? Tune in to today's episode to listen to what Daniel has to say about this matter. And now, without further ado, let me welcome him to the podcast. Hi, Daniel. How are you?
Hi, Miguel. I'm doing great. Thanks. How are you?
Very well. Thank you so much for joining us today. We're going to talk about a very exciting project in electric aviation. Very ambitious, I must say, because we've got quite a few companies developing electric aircraft here on this podcast. But the aircraft that you're designing, it's like let's say, super size for electric aviation, because it's really an aircraft that aims to challenge or to replace the conventional aircraft with a battery-powered electric aircraft, which is the Elysian E9X. But first of all, I think it would be great if we just start with just a short introduction about yourself and how you ended up leading this project.
Yeah, thank you, Miguel. It's a very personal project for me. So I started this actually together with 2 co-founders, but also with my father back in the day. And he has founded a company 40 years ago, Panta, which is very active in aerospace since that time, or for that entire time, which is, has touched on many aspects of aerospace, from operations to leasing to parts and components and maintenance. It's currently also the owner of Fokker Services Group, the former MRO arm, or still current MRO arm of the Fokker OEM, but now focusing, 80+% on the entire market, airlines, defense, private, etc. So I have a sort of deep connection, family connection with aerospace. My own kind of background is really to do with startups and tech. So I was working for Google for quite some years, and then was involved with a startup from the very beginning up to scale-up stage in digital video technology, something very different. Before I started working together with Panta on sustainable aircraft technologies. So really also applying some of that innovation experience into that family business. And what we found really important is to see how can we use our position, our connection, and our experience, and also, people and certification knowledge and things like that to do something good and to help accelerate, decarbonization of aerospace.
Yeah, actually, I wanted to ask you about this connection with Fokker, the very iconic Dutch aircraft maker brand, already a big force in aviation since the very, very early beginnings. I mean, I think the original Fokker started before the First World War, I think, right? Or something like that. Yeah, and then it stopped making planes, but then it became, as you mentioned, an MRO provider. Still quite a few Fokker aircraft around in the world, actually. Which I think they are being maintained as well by this company. And also, I think you mentioned Panta Holdings, right? It's the basically the parent company. Is it also an investor in other startup? I think the PAL-V flying car, is it also part of the portfolio? No.
No, PAL-V is not. But Panta does invest in startups, usually high tech, and also related to innovation that leads to decarbonization. Or so there is a battery company, a battery materials company called Imagy in the portfolio. There's also a space tech company. And a solar cell company. So those are relatively smaller investments or earlier stage investments. The main activities are, indeed Fokker Services Group and aerospace. And then within the sustainable technology side, various projects were started within Panta. One was in hydrogen fuel cell, one was in hydrogen combustion, and one was in electrification. And that last one is what turned out to be Elysian. So that was actually a collaboration between Panta, so the parent company, which I then was involved with, and Rob Wolleswinkel, who is my co-founder in Elysian, and who is leading the technical activities, together with then the third co-founder who joined a little bit later, Reiner de Vries, who is the chief engineer. But Rob had really come up with this idea that would it not be possible to design a larger aircraft, and is the assumption that it would never be possible not wrong, and have people not overlooked something by simply just trying to electrify turboprops and smaller aircraft, while not trying to start from scratch and look more at aircraft that can carry more energy weight. That was really at the core of it. And through that, we realized that there was really something there. And then also the Technical University in Delft and the professors there, after a meeting, concluded the same, that this is solid science. And, the impact is incredible, because if you can design an aircraft that can fly up to 1,000 kilometers, with 90 passengers, I mean, you're talking about almost half the world's flights and 20% of total CO2 emissions in aviation. So if you're considering, the gigaton of emissions of aerospace and the growth of the sector, clearly we thought, okay, there's something there, and we should continue with this. So we turned it then into a company, and well, the rest is history. So the three of us became co-founders, and that was a little bit more than 2.5 years ago.
Interesting. You founded the company in 2023, I think. And I remember at the time when it was announced that you were going for this project, I think you referred to a science paper that I think was from the University of Delft, right, that you mentioned, that was proving that actually it was feasible to make a relatively large aircraft power entirely by electric batteries. What can you tell us about the aircraft that you're designing, the E9X? Well, I will mention a few numbers that you have basically announced, disclosed. You're aiming to make an aircraft for up to 90 passengers and a range of 800 kilometers, which would make it an alternative for many flights in Europe, as you mentioned, like Amsterdam to London or Paris to Frankfurt. Many trunk routes could be covered potentially by this aircraft, right? Tell us more about the design and why you think this is feasible, because we're being told again and again that battery technology is not yet there. That's why most designs focus on the smaller aircraft, and even some companies have been kind of postponing plans to go electric because of waiting for technology in batteries to advance, etc. So tell us more about what you think is feasible and what are the other characteristics of this aircraft.
Yeah, of course. So indeed, we had always a very scientific approach. And when we came out into the open, that was early last year, we did that also at a scientific conference, the AIAA conference in Orlando. And our goal was really, okay, we need to first convince the academic community because they are the biggest critics. And of course, there was a huge amount of skepticism. Similarly, the Technical University of Delft was the first sort of group of academics that we managed to convince. And they were really skeptical at first. I mean, it was this very polarizing topic. And a lot of people were convinced that you could never fly commercially at those kind of ranges with those kind of passengers on batteries. And we published 2 papers. Our first paper was really about, okay, what are those misconceptions and why was something overlooked, which is that actually you need to skip the steps of smaller aircraft and maybe turboprops and very efficient aircraft today and go much bigger and use the weight of the energy, so the fact that batteries are bad energy sources, to your advantage by creating just a much larger plane, taking inspiration from other planes that have a relatively large energy weight or fuel weight versus their total weight. And then you get to aircraft like the old jets from the 60s, like the Boeing 707, or aircraft like the U-2 spy plane or the B-52 bombers. All examples of planes that had to fly far, that had to carry a lot of energy weight and had more weight than in their energy source than their total weight.
Actually, so, I like to mention those bombers from designs from the 1950s because when I look at your plane, I think there was an American bomber, I think in the design in the late 40s, early 50s. I think it was a B-36. Reminds me a little bit of the look of your plane. Of course, the technology is way different, but in terms of the overall layout of the design, it's something that is quite striking.
Yeah, so that's a really deliberate and indeed one of the most important observations that made this plane possible is that you need to do it in that way. And their reason for taking that much fuel with them was different than ours. Ours is just that's the only way to fly a range that is acceptable in a commercial setting. For them, of course, it was just the case that they needed to fly really far for a really long amount of time. And of course, at that time, planes were less fuel efficient than they are today. So that initial thought combined with a couple of other design choices, like putting the batteries in the wing, so making sure you put the weight where the lift is, you use that weight to your advantage. Having a backup system, so not carrying all this additional weight for your reserves, but solving that in a different way by having a fuel tank and a turbo generator. And a couple of other design choices like having distributed propulsion, so having multiple engines so you can optimize within that. So those are really core to the debunking the misconception. So that was the first paper, and it looked at different designs of up to 120 passengers and different ranges. And then the second paper was really looking at our design, so also derived from the requirements of how aircraft operates. So we always said okay, this aircraft is a commercial aircraft, it's a heavy aircraft, but because it's zero emission, it doesn't matter that it's very heavy. And the economics are relatively good because it has 90 passengers, and because of the cost of that, the battery cost curve versus that of fuel, especially if you include SAF and maintenance, the economics of this plane are relatively good. It still needs to be able to operate in an airport setting that is currently operated by narrow bodies, so by aircraft, the biggest aircraft that fly at those ranges. So some of the inputs to those requirements were, a 2,000-meter runway, 36-meter wingspan, so you fit into the gates. You don't need special gates or wide body gates and everything like that. And that led to this design. So a 90-passenger aircraft with an 800-kilometer initial range that is based on basically battery chemistries of today, but with some improvements, which we're expecting to be ready in about 3 years when we need it to certify it, and a really good economic profile, and some abilities to also have some technical benefits like reusable battery packs and some other elements.
The aircraft has 8 engines that are distributed propulsion. Where do you place the batteries? Do you place them in the fuselage? Do you place them next to each engine? Yeah, let's start by this. Where do you place the batteries? And then I will ask you as well about a few more questions about that.
Yeah, very, very core to the design is that the batteries are placed into the wing. So they are distributed across the wing box. And that also is very important in terms of making this aircraft possible. And it actually led to, and this is one of the studies we did in the last 2 years, our kind of hot potato studies. So deeper studies to actually further prove the validity of this design, which showed that the aerodynamics of doing it like that are actually really good. So there is also some aerodynamic benefits of putting batteries into the wing.
Why so, if I may ask?
Because you have a very large wing and a smaller fuselage, and it just allows because it's a very heavy wing, it allows for more control and a good aerodynamic profile.
Okay, sorry, I interrupted you. So you put the batteries in the wing, and what sort of technology you use for the batteries? Is it lithium ion, or you are aiming for some other more exotic chemistry?
Again, very deliberately chose to go for batteries, or to decide that this design needs to work based on batteries available today in production. So indeed, lithium ion with some improvements, with some new materials to make them more efficient, like silicon anodes and things like that, but really within that domain. And that's for a first generation. And within that, we think we can grow up to 800 kilometers, maybe a little bit more. If we really want to make the leap to 1,000 kilometers or more, you're talking about a second generation aircraft and new battery technologies. So we would be looking at more exotic chemistries. But we always said this aircraft needs to work with battery technology that's available today, with some improvements. And so that's what was achieved with this design.
But what sort of energy density are we talking about? Because I'm thinking, well, I mean, if just through a better design, it's possible to overcome this limitation with all this weight, energy density conundrum that the people that are trying to electrify aviation are facing. I mean, what sort of densities we're talking about, and why is it that not other people have thought about this, about doing this sort of design and just sorting it out?
Yeah, the energy density that we are expecting at, entry into service, but we need to certify it many years before. So we're taking a sort of 2028 moment where the battery technology needs to be ready. Our assumption is a 400 watt-hour per kilogram battery cell with 1,500 cycles. So the cycles are obviously very important as well, because there are already cells out there with higher energy densities, but they don't reach the cycle life. And so you always need to couple those things together. That is, I think, a quite realistic assumption, because, the battery technology now, it's about 300 watt-hour per kilogram cell. So with the batteries available today, if our aircraft could be entering the market today, you already have a range of maybe 500 kilometers. And so the strength of the E9X is really in the aircraft design. It's not relying on big leaps in battery technology. If those leaps happen, of course, the impact of the aircraft will be bigger and very welcome, but that's not the strength of the design. So we do believe that this aircraft will have an impact, and it is based on current battery technologies that will be available in the market. Then to your second question, why has nobody thought of it or tried to do it? I think it leads back to the points I made during my intro, that there was really this strong skepticism, which had less to do with expectations around battery technology and more to do with how the academic world was really looking at electrifying the best aircraft available in the market today through the assumption that because batteries are very heavy, you need a very light aircraft, or you need an aircraft that's very fuel efficient because batteries are a relatively fuel inefficient energy source. And that conclusion is, well, the fact that that is the case is the right conclusion. But everybody then concluded that, okay, battery electric will only be feasible for smaller aircraft or hybrid aircraft, and large will never be possible. And that sort of derived conclusion is the wrong conclusion. And of course, you can always look back and say, why did nobody think of it? I don't know. I think it might also be because there was just such a strong focus on other pathways to decarbonization. But yeah, as I said, it was an overlooked area, and we were the ones that came up with the idea. Well, as I said, Rob was the initial one that had this eye-opening moment. Mm-hmm. And then as we worked on it further and further, we realized that actually it is possible, and it is actually also a really good idea if you can make it happen.
And you are targeting a first flight for 2030 and an entry into service around 2033, right?
Correct. That is a timeline that assumes, of course, a lot of things fall into place at the right time. Mm-hmm. There are certain things that are in our control, and there are certain things that are out of our control. But this timeline is an ambitious timeline that is feasible if obviously the capital, but particularly also the certification, is ready and available when we need it. But indeed, yeah, that's our current planning is 2030 we start test flying with prototype. And then depending on certification, but the earliest we think we can enter into service is 3 to 4 years later, which is through the course of 2033.
Mm-hmm. And where are you now in terms of development?
We are currently going into in the preliminary design stage. So we are starting to build physical demonstration of our technologies. We now have a workshop up and running, and we are working on a couple of key demonstrators, including a full-scale wing segment mock-up with the battery systems in place, where we can showcase how this will work in practice in the aircraft. So this is on the ground, but it is a very large wing structure with the batteries incorporated there and the different systems running. And also, we will have in a couple of months our first skilled flight demonstration. So we will fly with a skill model of the aircraft. And there are a couple of other demonstrations we're doing. So we are really now starting to build the systems and the different elements of the aircraft separately to demonstrate those and bring them up in TRL level. Working towards in the next few years, the next phase, which would be the detailed design phase. But our really core focus now in this period is on those core technologies that make the E9X possible, and really bring those to the next level, because 80% of our aircraft is those core technologies. And then I'm really thinking about the battery pack, the wing integration of the battery pack, the distributed propulsion, so those 8 engines, as you mentioned, the high voltage system, and the reserve energy system. Those are the really core technological pillars that we're currently working on to bring.
I imagine the battery pack, you're outsourcing it to some external company. And then I guess you're leveraging as well the Fokker services expertise to do part of this technical work. Or am I right in assuming that?
So yes and no. The battery cells we are not doing ourselves. The battery modules we are currently developing with partners, but the battery pack and the battery wing integration is something we keep quite close to heart. There is a option that maybe we will collaborate on that with another party, but currently that work that I just mentioned, we are doing ourselves. We have engineers in-house with experience of designing and building battery pack and battery systems. So because it's so specific, because it's so new, because it needs to be tailored initially to our aircraft specifications, it makes sense to have that knowledge and capability in-house. Yeah.
And in your website, you use a concept, you talk about usable energy to the aircraft. Can you tell us a bit more what this means? Because you use that to compare to other technologies that are being right now developed to decarbonize aviation. And you show that by going electric, fully electric, you have more usable energy, which I guess has to do with the efficiency of electric motors. But can you elaborate a bit more about that?
Yeah, correct. Yeah, thanks for that question. It's really important and quite obvious, but often overlooked as well, that other decarbonization fuel sources or technologies actually require electricity to create, right? If you look at e-fuels or hydrogen, while both important pathways to decarbonization, if you really just compare them like for like with electrification, where electrification, of course, is only applicable to a certain range. I mean, there's always going to be a ceiling of how far you can fly with an electric aircraft. But if you purely look at, okay, from the grid to the actual engine, how much energy is retained after the whole process of generating it, storing it, transporting it, storing it again, and using it in the engine. With electrification, you really have very little loss because you're just going straight from grid, often to battery or to a mobile battery and then to a battery. So, if you compare that to, for example, sustainable aviation fuel or power to liquid eSAF, you have many steps in between that actually have a lot of loss of energy. And it has benefits, of course, it being drop-in and, you can use it straight away. You don't have to adapt engines too much. And of course, it has the main benefit that it allows you to fly any distance with it. But apart from that, it's a lot less efficient and so optimal way to use your electricity. And in a world where we have a major scarcity of electricity, if you can, for example, up to 1,000 kilometers, retain a lot more of your electricity, retain 80+% of your electricity versus 40+% of your electricity, of course you should do it because you can use that electricity in many other applications and also for using the SAF for longer distances.
There is another number that you quote in your website, which is basically the carbon intensity of the aircraft. Now, obviously, when we talk about direct emissions, it would be zero because it would be fully electric. But you have also calculated let's say, the carbon footprint of producing and operating this aircraft. You give a number which I think is on the border of around 40 grams of carbon per passenger and per kilometer. Is that right?
Yep.
And how you calculate this number? What sort of inputs go into this calculation?
So we did an extensive study that we commissioned to a research institute called CE Delft. And they looked at the life cycle of an E9X. So traveling with an electric aircraft like the E9X with all its specifications. And then indeed taking all of the different inputs in terms of manufacturing, battery swapping, and the actual aircraft itself, and comparing it with the other forms of transport you could take as a passenger. So other aircraft technologies like conventional narrowbody with normal fuel, conventional narrowbody with e-fuel, hydrogen options, and also an electric car with 4 passengers in it and an electric international train. And what came out of that study is that the E9X, there are different scenarios. So one looks at a 2035 scenario, which is a 75% green grid, and the other is a 2050 scenario, which is a 100% green grid. And so in the 2050 scenario, the E9X actually beats all other transport options per passenger in CO2 equivalent. It actually looks at CO2 equivalent, which is interesting, but also non-CO2 effects. And then the impact is even bigger. And in the 2035 scenario, it beats all other aircraft technologies and comes close to electric car and electric train, including infrastructure, right? That's very important to note.
Yeah.
But what the conclusion is that you can clearly show there, and there are a lot of inputs going into that and methodologies. I think it's now, we have too little time to really dive into it, but for anybody who's interested, we have the study on our website. So under the download section, you can go and download it, and the entire report is available there. And it's a very interesting read. Obviously important there is that you can make a case that it makes more sense to utilize existing airport infrastructure and an E9X aircraft in terms of sustainability than, it's more sustainable than, for example, investing in new train networks.
Yeah. Actually, that's a point that was made by another guest in this podcast, Dr. Klaus Rademacher, who has also calculated some of the carbon footprints of different modes of transportation, factoring in things like, as you mentioned, all the physical infrastructure that needs to be built to accommodate this movement of people, like could be trains, roads, etc. All right. So we're talking here about a range of 800 kilometers. So as we mentioned earlier, that it's pretty optimal for many of the routes that are inside Europe. But what about the size of the aircraft? What sort of feedback you're getting from the operators? Because what we are seeing now is that many airlines are upgrading to even larger aircraft. We're seeing companies like Wizz Air, for example, going for A321neo, so it's like 230 passengers, I think, or I don't know the exact number, but on that range. Also, many airlines going for larger versions of their single-aisle aircraft. Is 90 passengers enough to accommodate demand on all these intra-European routes? Some of them are really very dense. If we look at, Paris to Frankfurt, Paris to Berlin, Amsterdam to Munich. What's the feedback you're getting from the operators?
The operators are excited about this. We have a long-standing partnership with KLM, which also includes Transavia out of the group, where we look specifically also at some of these topics like the economic profile, new networks, etc. And now we have expanded that with a number of other top-tier airlines, some of which have joined our advisory group and some of which we're doing co-development with. The outcome is kind of the same, and that is, of course, before there hasn't been any electric aircraft that has been able to, where there was the ability to envision it in a current commercial network. I mean, it just hasn't existed. So for the first time here, you have a aircraft with a full electric range of 800 kilometers, which can be almost immediately placed. Of course, you need to have chargers at airports and stuff, but you can simulate it in a network of their current operations. And that is exciting, I think. Then from the economic perspective, we have done extensive modeling around the operational cost with inputs from different airlines, but also from our sister company, Fokker Services Group. And you can showcase that the economic profile per passenger, per seat, even though it is a 90-passenger plane, so it's a lot smaller than, for example, the 737s and the A320s that are often flying at short ranges as well, that it can come close and under certain conditions can even beat those larger aircraft. And that is, it is already an attractive aircraft if it can compete against similar sized aircraft. But if it can actually compete against larger aircraft, then it is a no-brainer, because then you have a lower operational cost or competitive operational cost, and you can operate in the same networks. I think more importantly of all of it, though, is flying has a popularity problem, right? I mean, airlines are under a lot of pressure from customers, from regulating bodies, from everyone, and they're being accused of greenwashing, and they're being accused of this and that. I think that aircraft haven't changed so much over the last decades, and new aircraft concepts are kind of many of them have not been directly applicable or operatable in their current markets. And I think this is sort of a solution that allows them also to look at how flying can get exciting again, and really have a more positive outlook for the future. So and I think that's somehow a bit more difficult with other fuel sources, for example.
So let's take, for example, the case where the alternative would be a 737. How cheaper is it to operate the E9X compared to a 737 in the typical configuration used in European short-haul routes?
Yeah, of course, it depends on how full the 737 is, right? But if you take a relatively full 737, the main underlying elements that will cause the E9X causes the E9X to outcompete are two parts of the cost breakdown. One is the maintenance and one is the energy. On the energy side, we expect the cost of the energy of the 737 to go up. Of course, you can have long discussions about the assumptions of that, but we use a very simple assumption in our CASK model and our cost per available seat kilometer model, which is that we expect the energy cost to double of the narrow body when we enter into service. So that's in 2033, 2035, like that kind of ballpark. Whether that's through mixing in SAF or charges or whatever reason, but that's the moment that we outcompete per passenger the narrow body. So that's perhaps not straight away, and perhaps initially it will be more on lower demand routes, but that's the core underlying assumption of when the E9X and how the E9X can beat the narrow bodies.
And how fast would be this plane compared to a 737?
It will be slightly slower. So it's essentially like a fast turboprop. And the speed will be around 650 kilometers per hour. On a average stage length that the E9X will fly, which is approximately 1 hour, the difference will be pretty small. It will be about a 5-minute additional travel time or something like that.
You mentioned, by the way, I forgot to ask, you mentioned another component of the cost savings, that's the maintenance. Is it obviously because of electric engines have less moving parts, or are there other elements there that you foresee are going to bring down the cost of maintenance? And how big that is in the total mix?
Yeah, I mean, it's less big than the energy part, but there's still a decrease. And it is indeed, a lot of it is about the amount of maintenance, and it's not just the engine, but the electrical powertrain needs versus the gas turbine combustion powertrain. And there our relationship with Fokker Services is very useful, because we could really go through all the different parts of the maintenance and the ATA chapters and look at real numbers and try to see, okay, this part we will not need at all. This part we will probably have less cost. So maybe we're assuming that 50% or 30%. And this part will be new, and then we need to make new assumptions. But indeed, the maintenance, there will be a lower maintenance cost.
There's another element of cost that I would like to touch upon, and that's basically, even if it's cheaper than operating an aircraft like a 737, even if it carries less people, if airlines have to serve the same sort of demand they are serving now with larger aircraft, plus all the extra demand that they might come, they will need more planes, right? How is additional capex factored in, even if, let's say, on a per capita basis, it can be advantageous, they will still need to buy more planes, right, to serve all this demand and invest in the hardware, basically.
Yeah, I mean, first off, there is a benefit to having 2 planes versus 1 for airlines, which is about flexibility. So, but if it is the same cost and everything's the same versus flying 2 planes versus 1, 2 planes is better, because you can be more flexible around distributing them across the network. Of course, there is maybe an argument to be made against in some countries, right? You have a limit on the amount of flights. Well, that would need to be then adjusted accordingly.
I was about to mention that, I think, for example, in the Netherlands is a case where they have put a cap on the number of operations, right? And then other places like Heathrow, it's not just a matter of flying X number of passengers, even if it's there are not so many emissions, but some airports are constrained in terms of capacity. Not all, I mean, but what's the approach here? Because I guess that could mean that some airports might not be that suitable for this type of aircraft, or certain routes
Yeah,
may not be that suitable.
I can't look into the future, but if I look at, for example, some of the large airports like the one here around the corner, you do see that they are also very keen to become more sustainable and decarbonize. And so I think there is a major incentive to allow, more flights. And you can imagine the policymakers that put these rules in place. If the aircraft, the reason is mainly twofold. One is emissions, right? The environment around here, and the other one is noise. And so, if both can be reduced by flying two aircraft versus one, it would be very counterintuitive if you benefit the aircraft with higher emission and higher noise. So clearly that would need to change, but it seems logical that there is an incentive to change that.
Yeah, but there's also the physical infrastructure constraint. I mean, some places that have like limited runway operations, also air traffic control. That will mean more planes on the sky as well. So I'm sure that's solvable. But have you factored this in these calculations?
Yeah, sure. I mean, from a cost perspective, yes. From an operational perspective, I mean, there's not much you can really factor in. It's more of a assumption that there would be at least a level playing field for sustainable aircraft, like literally zero emission aircraft, and of course also low emission aircraft. So I'm a little bit less worried about things like air traffic control. I think there are solutions for that, and well, here in the Netherlands is a very good example of how you can easily ramp up operations across a very large airport. Again, there are benefits because of flexibility, etc. And there are also routes that have simply lower demand. So, I mean, you're anyway going to need to think about those things. So,
True.
yes, they're factored in from a thought exercise perspective. And again, it's also not necessarily the case that all the flights we would do are most logical to do in Schiphol, right, in Amsterdam airports. It might also lead to new routes being developed that are more optimized, that have less nuisance for people living around the airports, again, because of noise profile. So I think it allows for optimization at a national or regional level.
You mentioned that you could potentially replace up to 50% of all passenger flights in Europe. What's the commercial perspective, and what is the let's say the related industrial plan? So let's say we are in 2033 and you've been successful with all the development stage, and you need to start delivering these aircraft to the airlines. What is your industrial plan? How many of these aircraft can you produce per year? And how many you think could the market potentially take from 2033 onwards?
That's a good question because, obviously there will be a ramp up period. So initially it will be a couple of dozen aircraft in the first year, and then it will ramp up from there. We have those numbers, but I don't really feel comfortable sharing them. I think maybe at a slightly higher level, we are really working towards that point of pre-industrialization, proving that these technologies are possible, and then taking it to the next level. Of course, starting to actually produce those aircraft is a major endeavor, which requires a huge amount of capital, which requires decisions of where to produce, with who to produce. Since we are in a very early stage of our development, like these are things that are modeled at a high level and where thoughts are shaped about how that might look, but it's not like a full-fledged plan is in place of how, where, and with who it will be produced, because this is quite far away and is dependent on many different things. There's also a scenario where maybe we do that together with someone, right? So I think that many options there. When it comes to the market demand, also there, I mean, the demand we see now from airlines in terms of how excited and interested they are, which we covered in a previous question, is clearly there. And, initially, in terms of a go-to-market strategy, you would look at replacing routes where regional aircraft we currently operate. You wouldn't start off by trying to replace narrow body straight away. And you would look at routes where you have the highest potential yield. So where the demands in terms of passenger demand quite closely aligns with the amount of passengers in this plane, and where maybe currently the airlines see a new opportunity to operate a route with this new aircraft. So those are all just to give you a sort of feeling for how you look at that kind of demand modeling and how the aircraft production might look from 2033. But yeah, it's too early to really give you concrete numbers or to get into that at this stage. That doesn't make too much sense.
From what you told me, I guess so far you've been funding this project through Panta, the investment company. But are you looking to raise more funds? Because as we were talking now, if this project continues, at some point it will need a huge amount of capital, right? To get through all the certification, build the industrial facilities, marketing, et cetera, et cetera. What is the financial perspective here? What is the plan?
Yeah, good question. We have two investors, so we raised around $10 million in seed funding until now, which is Panta with the initial investment and a French investor called Caravel, which is part of Clipper Group, and they have invested 5 million euros out of this seed round. We are currently in the process of raising a Series A1 round. And that's ongoing. Indeed, we will be raising additional funds for the upcoming years in different rounds. We're currently looking for investors that can contribute something and have a strategic relevance for us as well. So that's a big focus for adding new investors now.
Yeah. So talking about the market approach, you decided to focus on this, let's say, more mainstream segment of the airline industry. How do you see the landscape evolving for electric aircraft, let's say 10 years from now? Because there are other companies doing electric aircraft that are focusing on smaller aircraft, thinking here about aircraft that are in the range, let's say 9 to 19 passengers. Some others like Heart Aerospace, for example, going for hybrid electric on a 30, 40 passenger range. How do you see this electric aviation landscape evolving? And also, how would it cohabit with, let's say, more traditional fuel-based, could be SAF, but it's still like a fuel-based technologies that will, I guess, coexist at the same time? Are we going to have two separate ecosystems side by side? Because right now all the infrastructure is designed for one type of let's say, propulsion, right? I mean, you have turboprop jets, but they all take fuel. But in the future, you will have possibly these different technologies coexisting. Yeah, how you see the industry adapting to this?
Yeah, the technologies you mentioned, I think they push the technology further by a large amount. However, I think many of those, if not all, are always going to have a sort of more niche market application. So I think in terms of how many commercial aircraft of a smaller size, right, whether they're 9 or 19 or 30 passengers, can fly is clearly a lot smaller than if you look at commercial aircraft of airlines today or commercial networks of airlines today. So I think a more large-scale commercial solution is needed in order to have a significant impact, both from a climate perspective as well as it being commercially attractive enough for the airline to actually roll it out to replace the biggest culprits of emissions, which of course are in the narrow bodies and the regional jets, which are larger aircraft. Then like setting it off to the more hybrid solutions, even though those are, again, I think a very reasonable step in between. They only reduce CO2 emissions by a relatively smaller amount. So if you have a combustion fuel system combined with hybridization, so a battery that can allow for maybe 100, maybe more kilometers of flight or increase hybridization, you're talking 20, 30% maybe of CO2 reduction, where of course, the E9X is 100% CO2 reduction. So it's fully zero emission and no non-CO2 effects like contrails and like other like NOx effects and stuff like that as well, which is less researched, but still clearly going to have an impact. And we think that, we mentioned earlier that we think that our aircraft can have a potential impact of 20% CO2 reduction. If you include the non-CO2 effects, you can go up to 30%, which is very significant. And I think that, that is unique. I mean, there is no other aircraft at those ranges that can do that, except with the only exception of SAF. SAF is the only technology that can really claim to be able to reduce more than that, up to around 50% of the CO2 problem. But they don't tackle non-CO2 effects. So I think, that there is just a huge, let's say, benefit of actually being able to make this happen. And out of that sort of head start, so the fact that what we're doing was widely agreed not to be possible, it gives a sort of an ability for us to develop technologies underneath that make the electrification of aircraft possible in general. So I think a lot of the core technologies that we're developing, are leading to innovations already, like, for example, our battery pack, which has some really core innovations attached that will be likely applicable outside of our aircraft as well.
Mm-hmm.
So further contributing to the decarbonization and electrification of aerospace as a whole.
Well, if you succeed, you're going to have a virtual monopoly on this type of technology, let's say, right? So what are the next big milestones you have in store? What are the next stepping stones that we should keep an eye for?
Right now, we are focusing on doing physical demonstration of those core technologies. So that's one of the core focus areas. We are also working further on our certification, which is a very important challenge outside of the sort of core technical ones. So working more and more closely with EASA on identifying and solving the core certification challenges, and in our technical work incorporating those, and also taking the steps to create a certified organization, a design organization for ourselves. Further develop our commercial partnerships. So we have identified a product market fit in the sense that we have concrete interest from airlines, but we want to do that. We want to expand that more also on a global level. So really work with airlines in all the different regions, understand the different local needs and local demands, and be able to adapt the aircraft, or at least the conceptual basis of the aircraft based on that and all those different customers. We're also working on partnerships, so working together with suppliers, working together in consortia in terms of public funding opportunities and public programs that we're involved with. And really bringing everything to the next level to further prove this concept or this technology and this design in a technical, commercial, and operational sense.
Mm-hmm. Where can people learn more about Elysian and about the E9X? Also, you mentioned these scientific papers that you are using as the basis for your project. Where can people find out more about this?
Yeah, really good question. So on our website, elysianaircraft.com, we have a download section as part of the newsroom. All our papers are there with the entire technology explained and how we got to this technology. So we made a deliberate choice to republish and give a look under the hood of how it was possible. We did patent the technology first and got the patent granted. So, that also made us comfortable to do that. But I encourage anybody to have a look at that, particularly if they have a technical background, because it gives a really good idea of what the misconceptions were, how we debunked them, and how we got to our current design. Actually, maybe a funny anecdote is that we have assembled a very talented team from all over the world and from many different aerospace companies, the big traditional ones and also startups. And a lot of those people, particularly in the technical team, have really become enthusiastic about Elysian after reading the papers. So as part of our recruitment strategy, our recruiters would send the papers to people who were interested or who we were interested in recruiting. And through reading those papers, people got very excited about our company. And I think it's a nice testament of our scientific sort of DNA and foundation that we have that. We have this, we can actually back up our claims and we can send these papers around and show people how we did it, and not just, have the ideas, but also the backing.
Great. So I'm going to post a link to make sure that you get increasing the number of followers and enthusiasts that are following this project. Well, thank you so much, Daniel, for your time today. It's been great learning about this project, perhaps the most ambitious right now in terms of pure electric aviation, because of the size of scope what you're trying to do. Just left for me to wish you all the best with the next steps and the pursuit of this project. And I'll be keeping an eye on your developments. Thank you so much, Daniel.
Thank you, Miguel. Really enjoyed it.
If you like this podcast, you can support us by giving it a great rating on Apple, Spotify, or whichever platform you get it from. And remember, you can of course subscribe to it. And you can also get regular updates through the Allplane website. That's Allplane.tv. We have a newsletter where we cover the aviation industry every week with a special focus on innovation and sustainability. So give it a go. Thank you and goodbye.